a bit that looks like this. And these bits are arranged in pairs. And I have the pairs the wrong way around. As rungs in a ladder. An enormous number of rungs in the ladder. And what happens is the ladder is able to unzip in the ladder. And what happens is the ladder is able to unzip, and each half makes a copy of the other half. And that is how the nucleic acids reproduce themselves, and that is how we reproduce ourselves on the essential molecular level. The nucleic acid molecule itself, here is a very short piece of it, looks like this. And here, the various atoms have been compressed closer than in these models, so we don't have the little connections as we had in the previous model. And this is only about 2.5 loops or winds of this helical molecule. Imagine it going about 500 feet in the air, and you'll have a sense of what nucleic acid molecules are really about. Now, if I can surrender my nucleic acid extremely short molecule here, let us return to the question of the origin of life. How do we make such molecules? Well, noting that air is made of essentially the same atoms as most amino acids, maybe we would have the following idea. Let's take the molecules of air, nitrogen, oxygen, carbon dioxide, and water, put them together in a kind of flask, send some energy through the flask that'll tear atoms apart, and if we're very lucky, maybe the atoms will recombine in a way to make some nice amino acid. That would be very lucky. So let's do that. Here behind me is an experiment in which that is being done. This is an experiment first done by Stanley Miller in the early 1950s. Here we have a primitive ocean, extremely small ocean. It's boiling, water is rising, condenses in this flask, which contains the other molecules of air, and then circulates back through the ocean. Now we have to supply some energy. Maybe it would be ultraviolet light from the sun, maybe it would be an electrical spark. Let's do an electrical spark. Maestro. There. So now before your eyes, atoms of air are being torn apart, and the pieces are reassembling themselves. And if we let this go on for, about a few hours, we would have used up a lot of the air. What would we have made? Would we have made molecules useful for life? We would not have. We would, in fact, have made smog. We would have gone backwards from life instead of forwards. Well, let's reconsider the experiment. We started with air. Air contains oxygen. Oxygen is made by green plants. Could there be green plants before the origin of life? Unlikely, right? Because plants are alive. So we've made a silly mistake. We put in a product of life before there could have been life. Let us throw the oxygen away, do the experiment again with water, nitrogen, carbon dioxide. We will do that in the second experiment. Here, if we let this go for a few hours, we do make some molecules. We make formic acid, and we make formaldehyde. Now, because formaldehyde is used for preserving dead animals, you might think it's not too useful for life either. But that's not the case. Can I just get my ball? Thank you. Because if you have a lot of formaldehyde molecules and you let them sit together, they will spontaneously combine to form sugars. And you can see that it's a repetition of this same formaldehyde unit which makes sugar molecules. And sugars are very definitely part of what we're interested in. Sugars are part of the building blocks of the nucleic acids. So we've done something right. We just haven't done it enough. Now, to do it enough, we have to ask, what is it we just did between the first and second experiment? What we did is to have more hydrogen and less oxygen. If we look at typical organic molecules, we see lots of these little white spheres. organic molecules have lots of hydrogen. Maybe we should do this experiment with lots of hydrogen. But is that justified? Is there any reason to think that the early Earth had more hydrogen than today? Well, the early Earth formed out of typical cosmic matter, and we have to ask, what is the universe made out of? Does it have a lot of hydrogen or only a very little? Now, the way that scientists usually examine the stars, gas between the stars, planets, to see what they're made out of, is by spectroscopy. And here, what happens is light passes through a kind of slit, then through a prism, which breaks initially white light up into a kind of rainbow pattern. And here, we can have the lights down, we can see just such a thing happening in the apparatus that Mr. Coates is handling. This lovely rainbow is initially white light spread out into its constituent colors by a prism, an experiment first done by Isaac Newton. Now, if we take a particular kind of atom and send its light that it likes to shine through such a device called a spectrometer, we will get not a full rainbow, but a particular set of colors. So here we have the mercury atom, which is being induced by Mr. Coates to give off light. And that light comes in only 3 spectral lines that are strong here, a yellow one, a green one, and a purple one. If you saw such a spectrum coming from some object, you would say, my goodness, that object is made out of mercury. Now, in this way, we can look anywhere in the universe that's giving off light and have some idea of what its chemistry might be. So if we do that, we find a remarkable result. We find that almost anywhere we look, we see that the universe is red. This turns out to be a chemical, not a political remark. This is the Horsehead Nebula. You can see why it's called that. The dark cloud there looks like a horse's head. But the red gas that surrounds it is absolutely typical of what happens when you take long-time exposure photographs of virtually any place in the universe. And the next slide is another example. This is the Rosette Nebula. And it also is mostly glowing red. Hydrogen likes to give off a spectral line in the red, and that red line is seen almost everywhere. The sun is mostly made of hydrogen. The stars, the galaxies, the space between the stars, the big planets like Jupiter in our solar system. In fact, almost everything is made of hydrogen except the Earth. The Earth is almost the only funny thing around in terms of chemistry. Why? So, first of all, our assumption that the early Earth should have been rich in hydrogen is a perfectly good one. And before I return to the origin of life experiment, let me just ask this question. Why should the Earth, if it once had hydrogen, not have it today? And the answer is that hydrogen, the simplest, easiest molecule, used to be here, there it is, can run away into space. It is so light that if it's sitting around in the upper atmosphere of the Earth, it can be collided with by some other big, heavy, stolid molecule and made to move very fast. And if there are no other molecules in the way, and if it's moving at escape velocity, it will run away into space. The Earth's atmosphere, the upper atmosphere, is very hot, and it has very little gravity, and so, this is symbolic only, hydrogen will run away from the Earth. On the other hand, Jupiter has such a low temperature in its upper atmosphere and such a high gravity that not a single hydrogen molecule could have escaped from it in the entire history of the solar system. Now let us return to our experiments. Suppose we now mix together not